Yeah, my nose. And my chin. I'm not Christian anyways.
Okay, yeah, it's
I'm gonna ask yeah, my resident Aria speaking friend. Why you know go to DC? Well, you were there. The breeder was from what else? That was it.
Oh, I like it.
I'm the type of guy who can play 3 or 4 Why is that bad? Why? It's really serious and she's like crazy. I'm not sure. Do you think I'm listening? What do you think? You guys know
That's your crazy side. I don't think we know that.
Good evening. Teacher wants to wish you a good month. Have a good month. This is the first of the month, isn't it? March. So what we're going to do today, again, like the other time, we're going to follow the same format. We're going to go over an exam. The philosophy of the teacher is not to do a very large number of problems and not really to explain very well what we're doing. So we're going to do a number of problems. Basically, we're going to try to finish the last exam, the previous exam. So let's start. I'm going to use the document camera. It seems like most people prefer that than write on the board. Let's start first with part number 2 to do some arithmetic problems. So these are a few sessions about more or less equilibrium, right? In general, and then acid-base equilibrium. That's almost all of the buffer solutions. That's really on equilibrium. Okay, so let's start with the first one. Let's try to do this problem here. So this problem is giving us two chemical equations. We know the equilibrium constant of each. Let's say it's x and y. And then it is asking to find the equilibrium constant of another chemical equation. And applying the... Actually, what we're doing is based on the conservation of energy, even though it's not very clear to see it. We're going to see that later on when we talk about Gibbs energy. We're going to realize that what we do is valid because of the conservation of energy, actually. Now at this point it's not very clear to see why. But we know that if we manipulate the first two equations the problem is giving us in such a way that by adding them we can obtain this equation that we are looking to find the equilibrium constant, then we know that the equilibrium constant of the equation we are looking for, it will be the product of these two equilibrium constants, right? So the problem basically is how to manipulate these two equations by reversing, multiplying, the coefficients with a number, something like that, to be able to bring them to such a situation that when you add them, you receive this equation. Right? And then when we have these two equations ready to add, we know that the equilibrium constant K3 is going to be the product of the K1 times K2. Okay, so these problems are pretty actually interesting because you just have to really reasonably think what you need to do. You can memorize things here. So what we see is we want to create this equation from these two. Therefore, we have a 2a on the left. We have a 2a on the right. Well, there is no 2a here, so we can reverse this one. Double A will have the 2a on the left. Okay, so the first step is to go from the first equation. We don't need to carry the physical states, wasting time. It's not necessary for this kind of problem. 4b, 3d. In equilibrium with 2a, and has an equilibrium constant of K1 is equal to x. We see that we need to reverse the equation so we can have the 2a on the left. That's what we need. Okay, so we reverse it. And now this equation will have a new equilibrium constant. Let's call it K1 prime. And it's going to be the reverse of the previous one. So if this is x, this one will be 1 divided by x. Okay, we got the 2a, we won, and then what we're looking for, we want 4b and 9c. We have 4b, but we want 9c, and we have a 3d there, so we need another 6, we need another, let's see, we need 9c. This one has c, but it's 3, it's not 9. So if you multiply by 3 both sides by 3, we're going to have 9c that we need. Okay, so let's take this one and multiply by 3, the coefficients of it, right? So we take the second one, b goes to 3c, with equilibrium constant k1 is equal to y. And if we multiply by 3, y, because we need the 9c there, so by 3 is going to be 3d. Will give you 9c. And now we're going to have a new equilibrium constant, let's call it k2 prime, which is going to be, if we multiply by a number the coefficients of the equation, then we raise to that power the equilibrium constant. So this is, if this has y, when we multiply by 3, this is when y to 2. We are ready now to add, and these two equations, when we add them, right, what do we get? If we add these two equations, we're going to get 2a 3d and 3d goes away. So we have 2a in equilibrium with 4b plus 9c. And that's exactly what we wanted. We have it. And the equilibrium constant of this reaction, which is K3, is going to be equal to, when you add equations, the equilibrium constant of the resulting chemical equation will be the product of the equilibrium constants of the added chemical equation. So K3 is going to be K1 prime times K2 prime. Therefore, the equilibrium constant will have the value y to the q divided by x. So this is going to be the answer. There can be all kinds of problems, but the way of thinking is the same, right? This is the way to think. All right. Let's go to do the next one. The next one is about pH. Okay? So we have an aqueous solution which is 0.85 moles per liter in HCl, 0.15 in HBr, 10 to minus 8 order in hydrogen iodide, and 0.01 of hydrofluoric acid. So the pH of the solution at 25 degrees Celsius is. Okay? That's not really a hard problem, but if you remember what we said in the lecture, right? It's very easy to solve. When you have an aqueous solution, well, first of all, what do we want? We want the pH, right? If we want the pH, we actually need what we need is the concentration of hydronium ions total, coming from every source possible in equilibrium state. So now we're looking at how many sources we have that they can contribute to the total concentration of hydronium ions, right? And if you have an aqueous solution, the first thing you have is actually the water. So water as a source of hydronium ions will give you a concentration which, when it's pure, is 10 to minus 7. In the presence of strong acids, pretty well concentrated, I mean, you know, normal concentrations. 10 to minus 7 is going to be much less than 10 to minus 7, right? So the organization will be self-suppressed. So it's going to be less than 10 to minus 7. It's going to be 0.0000, so on and so forth. So this is basically, compared to these concentrations, 0.1 and 0.01, which two significant figures can be ignored. It's basically practically equal to 0. All right? Now, Let's see the acids we have there, because this is the other sources of hydronium ions. We can have, from the first one, HCl, hydrochloric acid, in other words, because it's a strong acid and it's a monoprotic. Therefore, 1 mole of HCl will give you 1 mole of H hydronium ions. So 0.85 will be H3O plus, right? So this is from water, this is from HCl, and that will be equal to 0.85 moles per liter. You agree with that? And then we have hydrobromic acid, that's a strong acid, and for the same reason, H3O plus from HBr is going to be equal to 0.15. Then we have hydroiodic acid, and from the hydroiodic acid, which is a strong acid, the concentration of H3O plus from hydrogen iodide will be equal to this concentration. But basically, compared to these numbers, is really practically equal to 0. It will not make any difference, you will see now. Okay, and then we have what else? We have hydrofluoric acid, and this H3O plus for the hydrofluoric acid is going to be practically 0 because it's a weak acid in the presence of strong acids with this kind of concentrations. It's going to be practically 0, suppressed ionization. So this is about practically 0. Okay? So you can see now that if we want the total concentration of hydronium ions will come from all these 5 sources. All these 5 chemical species contribute to the total concentration of hydronium ions. Now, these are about 0. 1, 2, 3 is about 0. So the only thing that really we care is these 3. Because if you add these 10 to minus 8, 0.0000, with 2 significant figures that you see here, you will only have these 2 numbers really to count for the total concentration of hydronium ions in equilibrium. So if you add these 2, how much do you get? If you add these 2, you will get 1. These 2 give you 1 moles per liter. And when you have 1 mole per liter, well, we go here, and that will be minus log of 1. Log of 1 is 0, minus 0, 0. So the pH of this solution is 0, right? Sometimes students think that the pH cannot be 0 for some reason, right? All right. About 9 o'clock, we're going to have a visit again. The 2 students will come and play us for 10 minutes some nice songs. If what? Loud, please.
If one of our acids were diaprotic and multiplied by 2.
If it was diaprotic, well, it depends. If it was, let's say, sulfuric acid, you cannot really do it because both of the ionization steps of sulfuric acid are not complete. They are not 100%. The first one is. So from that one, you will get as much concentration of sulfuric acid you have. Let's say 0.1, you will get 0.1 from the first ionization step, right? From the second one, which is weak, you will actually get practically 0 because it's a weak acid. HSO4 minus, it's a weak acid. Just like hydrochloric acid, kind of. And from that one, you will get practically 0 in the presence of the strong acid. So actually, you can consider it as that's a good question. You can consider it as a monoprotic acid, actually. You have sulfuric acid, right? There's no really acids that I can remember of to have both of the ionization steps to be strong. There's just, I cannot recall. You know? All of them are weak, sulfuric acid is a kind of an exception that the first one is strong, and then the other one is weak. Right? I just can't recall. Okay. Should we go for the next? Okay, the next one, it tells us to, it's a very simple problem about molarity, really. It's a cheap one, because there was an inspiration we were making it. That's why it's cheap, actually. Just a simple application of concentration in solutions, right? Salts. Okay, so we have an aqueous solution of 200 molar of calcium chloride as a soluble salt, and a known concentration in sodium chloride. So there is sodium chloride also, but we don't know the concentration of it. If the total concentration of the chloride ions is this, 0.05, then what is the concentration of the sodium ions? Right? You can solve it fast, you can solve it slowly, whatever you want to do. Let's see. We have two salts. You're talking about concentration of ions. Well, then let's dissociate them, right? So if we know we have calcium chloride, and when it dissociates, we don't put physical states to make things faster and simpler. So it will be calcium 2 plus 2Cl minus to be balanced. And if the concentration is 0.02 moles per liter, that means this is basically gone, right? There's no such a thing. It's gone, right? And actually what we're talking about when we say this, we actually have this, which is what? 1 gives you 1 and 2, therefore 0.02 will give you 0.02 and 0.04 m. So when we say we have this, we actually don't have this. We actually have that, right? Okay. And we have also sodium chloride. We have sodium chloride. Here is sodium chloride. And that dissociates according to this equation. And what we want to find out, the concentration of sodium ions. This concentration here, let's call it Y moles per liter, M. That's what we want to find out. When it dissociates, it's 1 to 1. So if you have Y of this from sodium chloride, you have also Y moles per liter from chlorides. And of course, the concentration of sodium chloride is also Y. So we don't know the concentration of sodium chloride. Let's say it's Y, right? 1 to 1 to 1, from 1 to 1, then Y, if it is Y, will give you Y and Y. Okay, so basically the question now in this problem is find out the number Y, isn't that right? Because what the concentration of what? Of sodium ions. We want the concentration of sodium ions, we'll call it Y, and that's what we'll find out, how much is Y. Okay? So, what do we know? What does it give us? It gives us something we didn't use it yet. It gives us the total concentration of chloride ions. That's given us, we didn't use it yet. We need to use it, right? So we have total concentration of chloride ions, concentration of chloride ions, total, right? We know it is equal to what? It is equal to the concentration that comes from what? Calcium chloride, and the concentration of chloride ions coming from sodium chloride, right? And that is gives us to be 0.08 moles per liter. Well, what do we know? We know that the concentration of the chlorides from calcium chloride is 0.05, right? So this one gives you 0.04 m, plus, we do not know this, that's what we're looking for, right? Y is equal to 0.08, and from here you can find Y. And remember, Y, as we said, is the concentration of sodium plus from sodium chloride, which is equal to the concentration of chlorides from sodium chloride. And that is, as we said, is 0.04. Your help. When the girls come to sing for you, you need to participate. Okay? Don't forget that. Right? They make this effort to come and reduce your stress and my stress. Right? We need to participate. It's good for us to participate. Right? Okay, let's go for the next one. Are you ready for the next one? Maybe we should do some exercise. Are you ready? If you don't respond, that means you are kind of in a state of a dormant state or something. Huh? You want to jump a little bit, something like that? You don't want to? You can do this work. How we're doing this in the meditation? We're in a meditation club with pocket and stuff, and we're doing the beginning like this. I am positive, energetic, and enthusiastic. And we do it several times. Can you do that? You want to do it? How many people want to do it? Let me see your hand. Okay, let's do it. Let's do it. I am positive, energetic, and enthusiastic. Right? I'm positive, energetic, and enthusiastic. Hey, you guys. You got to warm up the engine. Otherwise, if you go like this, it will never work. The car will not start. It's interesting to see, professors and staff. Wednesday, 12 to 1. So we do this childish stuff. Why? Because it works. That's why we do it. Because thousands of people and millions of people around the world, they have discovered it works. That's why they do it. So you see old people, 70 years old, they're staff, they're professors, whatever, and they're just doing that. And then meditation. It's reality, okay? So maybe at the end we're going to do that before you go home. Okay, let's do the next problem. So we have a very concentrated solution of a base, and we know the pH. What is the molarity? Usually the problems in most textbooks is the other way around. They give you the concentration of the base, and they ask you the pH or the pOH. Now, this is the reverse. So let's see how we're going to do that. We know the pH, and we want to find out the molarity of the solution, right? This is already something that I'm not sure if you really have noticed it, but this is an incredible, powerful tool to think about when you solve problems in science and in general. There's three main ways to solve problems. It's a very general comment up here, okay? So when you have a problem to solve, you want to go from A to D. Okay? You know this, you know this, and you do not know this. So you want to go from something you know to something you do not know. Okay? This is very important, pay attention, because many times it will help you to solve problems you would not be able to solve otherwise. And in fact, this method is used all the time when you take organic chemistry to write mechanisms and all kinds of things in organic chemistry. Okay? So to go from A to D, there's 2 ways to do it, 3 ways to do it. Sometimes it is easy to say, okay, I know A, so okay, if I know A, then I know B. And because I know B, I know an equation that relates B and C, so I know C. And then I know another thing that C and D relate, okay, so I can go from C to D. That's going forward. Some problems are solved that way. Some other problems you cannot go this way because you cannot see this step. So you cannot start. But you can go backwards. So you can say, I want to know D. So if I want to know D, if I want to know D, then I just know it's related to C. So okay, I know I can go from C to D. So now, if I know C, right? If I know C, does that relate to what? Oh, that relates to something which is called B. And then, I don't know the relation between B and A. Okay, or something like that, and you go like this. So this is called forward, and this is called backwards. This is going backwards. Actually, I should put this way. And a third way of solving it is you can start forward, and you go up to a point, and you say, I don't know how to go farther anymore. You're stuck. So you start the other way, and you go backwards, and you meet somewhere here, and then you know how to solve the problem. These kind of methods, the 3 methods, are actually in the reader in the first pages. When it says how you study, how many people have noticed this? There, let me see your hands. Okay, good for you. Because this is really the way you solve problems. They will fall into this category of these 3 categories, one of them. And let's apply this now into this problem. In this case, it is easier to go forward, right? So we know what we have. What do we have? The problem is giving us pH to be 15. Okay? So from there, we're going to try to find out the concentration. This is what we want to find out. We want to find out the concentration, molarity of this base. This is what we're looking for, and the only thing we have is the pH. Interesting, right? So we have the pH and we want to find this one. To go and start from here backwards, in this case, doesn't help. I know pH. When I know pH, what do I know? I know that this is minus log of concentration of hydronium ions. That's 15. Okay? Well, that means I can solve this equation very easily with my calculator, and then I have the concentration of hydronium ions to be, that's concentration equal equilibrium total. This is, usually the textbooks don't put this, but when you learn, you really need it. And then if you learn for years, whatever, then it's okay, but you're really learning now, so it should have been there in the textbooks actually. I found it very necessary when I was a student. I didn't have it. So it's good to really realize what this is. When we talk about pH, we have the total H3O plus at equilibrium state. All the systems are equilibrium. And so this is equal to 1.0 times 10 to minus 15. Okay, so we know the concentration of hydronium ions. Now, if you know the concentration of hydronium ions, we want to go into base, right? Base. And base has OH minus. The two, H3O plus and OH minus, relate to each other. How? Well, they are ion product of water, right? So from ion product of water, we know that we always have concentration of H3O plus at equilibrium times concentration of H minus at equilibrium, and that's total, right? Total. Whatever sources there are there, it's the total. This is not in the textbook, so it's really confusing until you realize these things. You know, if nobody tells you, it will take you years to really figure these things out, how they work. You know, this is at 25 degrees Celsius, 1 times 10 to minus 14. Okay, great. Look, what the concentration of OH minus is equilibrium total. It will be 1.0 times 10 to 14 minus 14 divided by 1.0 times 10 to minus 15. So it turns out to be 10 M. Okay. So we know the concentration of the hydroxide ions in equilibrium. Total. Why do we say total? Because we have hydroxide ions from where? From the water, and also we have from the base. Is that right? So, concentration of hydroxide ions in equilibrium total, it will be equal to concentration of hydroxides. They come out from the source of the strong base, and we have hydroxide ions that come from water. You agree with that? And because we have a strong base, concentrated, the transition of water is fully suppressed. Practically speaking, the concentration of this is going to be equal to 0 from water. So, we have this relationship then, right here, which tells us that the concentration of hydroxides that come from the base is actually equal to the concentration of hydroxides that comes from equilibrium total, which we know already, we said, is how much? 10. Okay, great. So we are close to what we want. We have the concentration of H minus comes from the base. We want the concentration of the base, and it's a strong one. Well, you can imagine what it is, but some students have a problem to really see why the concentration of this is going to be, how much it's going to be. So, concentration of the base, that means moles per liter. What moles? Moles of formula units. This is moles of hydroxide ions per liter. It's 10. 10 moles of these hydroxide ions per liter. We want the concentration of the base. That means how many moles of these formula units dissolved in 1 liter of solution. Yes? Alright. So how much will that be? Can you see why it will be? How much it will be? 5? Okay, so some people see it really fast. How many people want me to show you why it's 5? Let me see your hands. Just raise it. If you don't understand why it's 5, raise it now so you will know, otherwise you will not know. I will not go over it. Okay, it's about 30–40% people that they want to know. Look. It's really, look, you have this base, yes, you have this base, and the ratio of particles, right, is this. You got 1 formula unit of this per how many hydroxides? Per 2 hydroxide ions. Formula units, you see it as a particle. And hydroxide ion, you see it as a particle. So the ratio of these two particles is 1 to 2. You remember? Number of moles is equal to number of particles divided by Avogadro's number. Yes? And for that reason, the ratio of particles also, you know, equal to what? To the ratio of moles. Is that right? So it's going to be 1 mole of formula units of this, divided by 2 moles of hydroxide ions. From the formula, you have this, because of this equation, they all lose the ratio of particles, also the ratio of moles. So what do we have? We have 1 mole of this per 2 moles of that. Yes? They are in the same solution, in the same volume of solution. When you have particles in the same volume of solution, always the ratio of moles is also the ratio of concentrations. So this one is equal to the concentration molarity of this divided by the concentration of H minus 1/2. And from this one, if you solve for this one here, you will have what that is 2 times that, which we know it's 10, 2 times, wait. What am I doing? 1 to 2. Okay, 1 to 2. What we want? We want this. Okay, so this one will be, this is the mistake I made. This one is going to be this divided by 2, not times 2. Okay, so it's going to be 10 divided by 2 is equal to 5. Okay. Another way to see this, that the ratio of moles is also the ratio of concentrations. Instead of saying it's in the same volume of solution, right? You can divide by the volume of the solution, both of them, and you have the concentrations, right? Everybody got it now? Okay. Are you ready for the next problem? Okay, let's do this problem. So we have to, this problem is going to calculate the pOH of an aqueous solution of a base. We will know the concentration and we know the Kb of the base. That means it's a weak base. If you have an equilibrium constant, it's a weak base. What is percent ionization besides the pOH? And this is interesting questions here. If you add this salt or that salt, what will happen to the pH? Okay, so let's see it. Quite a few questions, right? All right. Let's start from the first one. What do we have? If you have a base in water with Kb whatever, that means you have a weak base. So this is the problem to calculate pH or pOH of a weak base in water, right? Remember that? And the way we do it is you do an ice table, right? And you find the pOH or pH. But we said in the lecture you can do it really fast, right? Much faster. So the only thing you have to do is to know 2 things. The equilibrium constant and the molarity. Okay, so molarity in this case of the base, Mb, is equal to how much? Is 4.0 times 10 to minus 2. And then you also have the equilibrium constant Kb is equal to 1.0 times 10 to minus 4. And in order to use that simple equation without wasting our time to do ice tables, the only thing you have to check is, remember Maca, and then Mb, Kb, right? So the ratio Mb to Kb should be what? Should be larger than 100. This is very easy to see actually. You don't even have to do it during the exam. 100, right? It's really funny, huh? So if you put the values, right? you can see that this is 4 times. The only thing you look is the order. Second order, that's 100. Yes. Okay, so if that's true, then we don't have to do that stable. You can use the equation. We're talking about a base. So if you talk about the base, then you say hydroxide ions at equilibrium total will be equal to square root MB times KB. And if you put the values, you do the calculations, you find out 2.0 times 10 to minus 3. Okay, so we found the the hydroxide concentration, equilibrium total, right? And that's going to give us the pOH, right? We can have the pOH. pOH is going to be equal to minus log of concentration H minus. So it's going to be minus log of 2.0 times 10 to minus 3, that's it, and that will give you 2.7. Okay, we found the pOH. That's the first question of the problem. Okay, the second question is, what is percent ionization? Okay, somebody can do really this fast, if you are experienced, right? But we're not experienced that much yet. So let's see how we're doing it, right? In a little bit slow pace. To understand it, it's better to write the equation down. When you get acquainted with this really good, then you can do it really fast, just like that. But we're not at that point yet. So let's write the equation down. So the equation will be, this is B. So B is the base, whatever it is, we don't care. And that will react with water to give you the cation and OH minus. Okay, what do we want? Percent ionization. So we go to the definition. What is percent ionization? Percent ionization will be equal to the number of molecules of the base that ionized divided by the total number of molecules of base that I have in the solution. Total, I put in from the beginning. Because the ratio of molecules is the ratio of moles, the ratio of moles is the ratio of concentrations, because both particles are in the same solution, right? Instead of talking about molecules, we can talk about concentration. So actually, we need the concentration of the molecules of B ionized divided by the molarity of the base total. What we put in originally, right? How much we dissolved in, right? How many moles per liter we dissolved. Do you agree with that? That's a fraction. And if we want percent, that should be 100 times 100. Okay, now, I want you to understand this. When we say ionized, right? When we say ionized, is actually the concentration of BH plus, isn't it? How much they broke, were ionized actually, that's the problem, is equal to the concentration of that Y. Because one of these gives you one of that. So if one of these reacts, will give you one of these. So the concentration that they reacted with water, is going to be equal to this concentration. So instead of this, I can write the concentration of BH plus in equilibrium. Because this and this is the same. Divided by the concentration of B, total, let's put original, that circle there. You can leave it the same way, it doesn't matter. Times 100. Okay, now we are closer. You can see now that the concentration of BH plus equilibrium, still we have a little bit more work to do. Because usually books will just give you the numbers like this, they won't explain to you how it happened, really. Do you know the concentration of this? Of BH plus equilibrium. You know it. What is it? How much is it? How much is it? 2.0 times 10 to the minus 3. Why is that? How many people want to know why it's 2.0 times 10 to the minus 3? This concentration here. How many people want to know why? Raise your hands. If you know, don't raise your hands. If you don't, raise it so you will know. Again, about 40%. Okay, so this is the reason why. This is the reason why. When you have an aqua solution, right, it is assumed it's neutral, right? The total plus charge is equal to the total minus charge. Some people, they might think they know, but they really do not know. I'll ask you a different question before. Now, how many people really they do not know? So I want you to be honest to raise your hand so I understand what's going on. That improves the teaching. When you have an aqua solution with all kinds of ions, cations and ions, right? The total, which assume it's neutral, the total number of plus charges is equal to the total number of minus charges. By just applying that very principal idea, we can answer the question why this to this. That's the only ion that you have. Hydroxide ions, hydronium ions, and BH+. Is that right? Do you have anything else? That's it. So because each one of them has one charge, it's not 2 or 3 charge, that's why it has to be concentration of OH minus from water plus concentration OH minus from the base, the weak base, right? This one and that one should be equal to concentration of H3O plus, of course from water. We don't need to say it, but for the sake of making things clear, because there's only one source of hydrogen ion, plus concentration of BH plus. Now, look at this, because like the teacher said, most books will not tell you why. You just make it, it's equal. Why it's equal? So this is true, right? This equation actually gets a little bit complicated if you have charges. So if it was a minus 3 here, let's say it was phosphate, right? There was a minus 3 there, then you would multiply it by 3. This is an easy thing because they're all single charge, right? But if it happens to be the ions, they have 3, minus 2, or minus 3, or plus 2, then you multiply this concentration by that coefficient. Think about it. Okay? In this case, we don't need to multiply it. Welcome.
Hello.
Okay, just a little bit and we'll be ready. So this is true. You understand why this is true, right? So, but look at this. We have a base, right? Weak or strong, it doesn't matter. And it's not a very dilute, very low concentration. It's 10 to minus 2. That's pretty good concentration from what we know from our class, right? So the ionization of water is practically suppressed, right? That means the concentration of this and that, they both come from water, don't they? They are less than 10 to minus 7, right? In fact, what we're saying, we don't have to say that they're small, actually. We say they're equal at this time for this problem. They're equal, are they? When water ionizes, right, the concentration of H2O plus, which minus comes from water, they're equal, always, right? So actually this goes away with this. And then what do you have? You have the concentration of BH plus is equal to the OH minus from the base. That's what we wanted to prove. So instead this, we put what? The OH minus from the base, which is how much? The OH minus? 2.0 times 10 to minus 3 divided by the concentration of the base, which is 4.0 times 100, and that's 5% ionization. Great. Everybody got it? Let me see your hand. Next question. Before we explain why these two concentrations were equal, how many people really did not know, but now they know because we explained that equation? Let me see your hands. I'm curious, just curious. Just student. Okay. It's about 50%. So you see, many times we think you understand or know something, but you don't. So it's good to the teacher to know what's going on. That's why, please raise your hand, right? Okay. And let's do the other two parts. It will not take a long time, and then we'll. So we won't cut the problem in the middle. Okay. So the next question is. If you add to the solution, that's a solution. It really doesn't matter what the solution is, right? Can you see that? If you add to this solution a few crystals of sodium hydrogen sulfate, will the pH increase or decrease? It's a weak base, we don't know what it is. So that problem cannot be having to do anything with common ion effect because I don't know what the base is. So how can I talk about common ion effect? So, in general, we have a basic solution, right? And you put sodium hydrogen sulfate, what will happen to the pH? Will go down or up? That will become towards acidic or towards basic, right? Down, up. How will you answer that question? This is actually a good question. How do you answer that question? The question if the pH will go up or down depends on what the salt is, acidic, basic, or neutral, is that right? So if the salt is neutral when you put it, and the ions of the salt will not react with water, the pH is going to stay the same. Is that right? If the salt that you put is acidic, the pH is going to go down, and if it's basic. So the question actually is, to answer the C question, is this. Sodium hydrogen sulfate. What is it? What is it? Basic? Acidic? Neutral? What is it? Okay? And in the reader there's a good portion there that deals quite good with this topic. How to decide a salt if it's going to give you acidic, basic, or neutral solution. Yes? Okay? So the way you do it is you see the two ions that they're made of. So this salt is made up of two ions. Which are the two ions that it's made? Sodium plus and hydrogen sulfate. Yes? So now you question yourself, will any of these two ions, or both, react with water? Yes or no? So this one with water, you know that it does not react. Sodium reacts, sodium atoms, metal reacts, but sodium plus does not react. It's already 8 bonds in the outer shell, so no reaction. But this one, we do not know yet, we'll see, right? So we have hydrogen sulfate. Now this one needs a little bit thinking here because hydrogen sulfate is actually an amphoteric chemical species. That means it can go either way. You realize this? It can act as a prosperity acid, but also it can act as a prosperity base. You can pick up a proton from water, potentially, right? Potentially. We're looking at the possibilities. You can pick up a proton from the water, acting as a base, and that will make it this way, plus OH minus. Or another possibility is to act as an acid, and in fact to give a proton to water. So here a proton goes this way, here a proton goes that way. So if this acts as an acid, prostonary acid, it will become as sulfate ion and hydronium ion. Okay. Both are possibilities, reacting with water, right? So the question now is, which is true here? Is this possible? This, that, both, or not? None of them possible. What is going on? Anybody? Is the first one possible? How many people say the first one is possible? Let's see your hands. How many people say the first one is possible? Let's see your hands. How many they say the second one is possible? Let me see your hands. How many people do not know? Let me see your hands. Interesting. Look at this. Hydrogen sulfate with water will produce what? H2SO4? H2SO4 cannot exist in water. When you put water, it's a strong acid. the first ionization of sulfuric acid is 100% reaction, it's a quantitative reaction. Yes? HSO4 minus reaction with water, and it gives you sulfates and hydrogen ions, and that's a weak acid, has a Ka, A2, right? So this one is not possible. That's 0% reaction. Okay? This, although, is possible. And if this is possible, then it creates what? Hydronium ions. That means sodium hydrogen sulfate is acidic. Therefore, the pH is going to go down. Okay, great. Now, the last one is very easy. You can answer it in a few seconds. And that is, what will happen to the pH of solution if you add a few crystals of sodium chloride? Okay, so that doesn't really need much explanation. Sodium chloride comes from what? You want me to explain it or not? How many people want me to explain it? Okay, well, I see. Again, it's the same question. We have sodium chloride, right? And we want to know what will happen to the pH when you put it into the solution. Again, what is sodium chloride? Is basic, acidic, or neutral? What is it? Okay? Separated into ions. This salt actually comes from what? From a strong base, this one here, and a strong acid, this one, isn't it? When it comes from a strong acid and a strong base, the salt does not hydrolyze. That means its ions do not react with water. You can see it in another way. You can see it in another way that the sodium chloride, you can see it in another way. Huh, do you like that one? That's pretty easy. Nice, huh? For first time came out like that. For first time in my teaching lifetime. Really. It's pretty cute. You can see it's sodium plus and Cl minus. Right? It's pretty easy, huh? Nice. I like this to be in the reader because it's really easy to remember and understand, isn't it? Maybe next time I can do it that way. Now, this one, you ask yourself, does that react with water? Does this react with water? If it does, it will create what? No, it does not react. We said that. We explained in lecture why it does not react, right? Sodium plus does not react with water. You get hydrate, but does not react with water. No covalent bonds with oxygen. And this one, if it does react, it will give you HCl. But that's a strong acid, just like the same case with sulfuric acid, the first. Remember? So that's not possible either. Therefore, because they don't react with water, or you can say it comes from a strong acid, strong base, that's why sodium chloride will not, it's a neutral salt, and therefore when you put it in any solution, the pH is going to stay same. Right? Great. You see, I'm equipped. Look at this. Which songs I can use? Alright. Okay, I'll use it over. So yours.
So in the question you actually asked, if you add it to the solution, but the NaCl is already, it's neutral, but the solution is already basic, right? So doesn't that mean that the solution will be basic, not neutral?
The solution is basic. Whatever it is, doesn't matter. Basic, acidic, it doesn't matter. What you put in, what will create? OH minus, H0 plus, or none of them. Okay? And we cannot talk about common ion effect in this case because we don't know what the base is, so we ignore that. Right? What is the nature? Right? The base we don't know. So we don't know if there's an ion common ion effect affecting the pH, what will happen. So if we do not know that, whatever the salt is, that's going to happen to the pH, right?
Good luck on your midterm.
They will do better now because they will not have a stress otherwise, right? You will do better because now you will not be stressed. You will think about these moments, okay? All right. So let's do a few more problems at a time. So let's do this problem here. Okay, this problem is it's an equilibrium problem again. Calculate the equilibrium constant Kc. That means it refers to molarities, right? Kc refers to molarities, concentration molarities. You should have said Km. C is concentration in general. Anyway, we know that it means molarities, right? If we know so many moles of A, so many moles of C, it doesn't say anything about B. So that means it's 0. And allowed to reach equilibrium, the amount of B in equilibrium is 1.5 moles. So to solve these problems with equilibrium, that involve the chemical equation. We write the chemical equation, we do the ice table more or less, right? You know that, right? So let's see how we're going to do this. We write the chemical equation. We have 2A goes into B and C. We write them a little bit separated so we can work out really easily without becoming messy, sloppy. So you give space to it. Okay, and we do the ice table. So initial concentrations will be, 8 moles of A. We have C, 5.3 moles. And it doesn't talk anything about B, so I assume it's 0. We don't have any B. So 0 moles initially of B. Okay, now, we want to find out Kc. That means we need the equilibrium concentrations of these species, right? Concentration when the system reaches equilibrium. Apparently the system is not in equilibrium. Why it's not in equilibrium? Why? You can calculate Q. Q is going to be this times that divided by that. Q is 0, right? The system has some equilibrium constant, so it will shift to equilibrium, so the 0 will become equal to the equilibrium constant, all right? Or you can follow this general rule. Whenever you have one component that is 0, the system will shift towards that direction. So sum of A will break down into B and C until it reaches equilibrium, yes? So we know it's going to go from left to right. We know that. But whenever it's 0, it's going to go towards there, period. Okay, so if that's the case, then sum of A will break down, sum of B will form, and sum of C will form. Now, we're going to call, we don't know how much is going to happen, how many moles will break down. We call Y the unknown. Usually, it's easier to make calculations. You still can get the same number, but it's easier to, for the sake of calculations, to call the unknown the species that has coefficient equal to 1. Okay? So I'm not going to call Y moles of A broke. I would say Y moles of B formed. That's the change, C. So, Y moles of B were formed until it reached equilibrium state, because when one forms, another one of C is forming, therefore we have Y moles also of C. Y moles of C were forming because it's 1 to 1, Y 1. From the ratio of 2 to 1, when 2 react, they give you 1B. When Y came, how many A's reacted? To Y, right? And that's minus because it's a reduction in concentration. Minus 2 Y moles. Okay, and equilibrium, therefore, very easy now, is going to be what? In equilibrium, we're going to have 8 minus 2Y, and this is going to be Y, and this is going to be the sum of this, the sum of this, and the sum of that. So this one is going to be Y plus 5.3. These are the equilibrium concentrations, right? And if we knew these values, then we have the Kc. But we don't. What do we know? We know that the equilibrium concentration of B is how much? 1.5. This Y here is actually equilibrium number of moles for B, isn't it? Okay, so that Y is actually 1.5. So I can write this line equilibrium and say Y, we know from the problem, is 1.5. If Y is 1.5, then we know also this, because they are a function of Y. So this is going to be 5.3 plus 1.5. And this is going to be 8 minus 2 times 1.5. So if I want to write again, equilibrium is going to be 5.0 moles. You do the calculations. 1.5 moles and 6.8 moles. So when we found the number of moles at equilibrium state of each one species, right? So now we want the equilibrium constant. Now you have to be careful here, right? The equilibrium constant Kc, let's write it. These are all gases, right? These are all gases. So Kc by definition is concentration of B Molarity, yes? Molarity. Times concentration of C at equilibrium divided by concentration of A, equilibrium to square. These are molarities, right? Kc is molarities, concentration. It's no number of moles. In this case, it doesn't really matter. Why? Because the concentration, you see, we have the number of moles, but we don't have the volume. How are we going to find concentration? Listen to this observation. Whenever you have a system like this, a delta mg is equal to 0, you can calculate delta mg here, right? You know how to do that. Delta mg is equal to 0. If that's the case, then K as a function of concentrations is equal to K as a function of number of moles. And you will see now why. Look at this Y. The concentration of B is going to be actually what? Number of moles of B. How much is it? Where's B? Here, right here. So it's going to be 1.5 divided by the volume of the container. Isn't that right? Well, because we want concentration of Kc. Times concentration of C, how much is it? 6.8 divided by the volume of the container, because we want concentration. We do not know the B, but that's supposed to be. And then A is going to be what? A is 5.0 divided by volume to square. We want to find Kc. Can you see that the volume goes away? Yes? V times V makes V square here and goes away. So we don't need to know what the volume of V. So you can find out that Kc is equal to 0.41. If this one here, there was 3, instead 2, there was a 3 there, you will not be able to calculate Kc unless you know the volume. Then you will have to plug the volume there to be able to find the Kc. Can you see that? Okay, let's go and do now the concept. Should we go with the concept? Huh? Okay, let's do the first one. So what do you think the answer is? Think about it. We have a chemical equation describing a chemical system, a general chemical system, which is reversible chemical system. We have the chemical equation, and it says to choose the correct one thing here. Okay? All right, the first thing you need to do is what? Is delta mg equal to 1? No, delta mg. How many people want me to do the delta mg? Raise your hands. To find delta mg. You know how to do it. We talked about it in the lecture, right? Okay, we don't need to do it. So delta mg here is what? 0, right? Delta mg is 0. So we have volume change and temperature, okay? It's gases, so the volume can affect the position of the equilibrium, right? The volume and temperature. Okay? Increasing the volume will increase the amount of C. Here is C. Increasing the volume. If you increase the volume, right, the pressure is going to go down. But the pressure likes to be the way it was. So some more will be produced. Which one will 2 and 3 and 3? It really doesn't produce. Both reactions give you 3 moles, so what does that mean? That the volume will not affect the position of the equilibrium, and therefore the relative amounts, and therefore the relative amounts of the gases. Be careful, the relative amount. You didn't say something else. We're going to see it later. Increase the volume, again, so changing the volume, nothing will happen because delta mg is equal to 0. When you have delta mg is equal to 0, the position of the equilibrium will not change. The relative amounts will not change. Increase in temperature will decrease the K. Well, let's see. It's an endothermic reaction. When we say endothermic reaction, the books really sometimes they don't clarify this. We mean, and they don't say it, is a forward reaction. Okay? So when you say the expression, this reaction is endothermic, it really means the forward, because there's two reactions here, the forward and the reverse, right? So when it says it's endothermic, we mean the forward is endothermic, right? So if you increase the temperature, so more of this, right, you will push it this way, because the system doesn't like that higher temperature. It's going to somehow absorb it. How is it going to absorb it? Going this way or that way? Of course that way. So by going that way, the equilibrium constant is going to increase, because you will have more of this and less of this. So the equilibrium constant is going to increase if you increase the temperature. So cannot be D. And then he says decreasing the volume will increase the concentration of all gases. Well, that's true. If you decrease the volume, all the concentration will increase. Right? Do you agree with that? The position of equilibrium is going to stay the same. The relative amounts in moles, in grams, is going to stay the same. Right? But the position of equilibrium, but the concentration is going to increase. Because you have less volume, the concentration will go up. Why the equilibrium constant does not change? Because delta Ng is equal to 0. And the volume will go away again. Right? So that's why, by changing the volume, the position of equilibrium is not going to change. Right? Okay, let's go to the next one. So the answer is E. Okay, let's go to the next one. This is similar. It's applying the Chatelier principle, right? So which of the following will cause the position of the equilibrium to shift to the left? So we want the position of equilibrium to go to the left. This way, that way. So we want to shift the reverse reaction to take place as a net result, right? Adding a catalyst while the available volume of the gas stays the same. No, why not? The catalyst does not affect the position of the equilibrium. It does not affect the relative amounts of reactants and products. It does not affect the yield of the reaction, right? Okay. Decreasing the volume of the container. Let's see. You have gases here, two gases. If you decrease the volume of the container, decrease the volume, the pressure goes up. You don't want that high pressure. Which way will move to make the number of particles less? This way. So it's going to go to the left, right? So the answer should be correct B, right? If you want to confirm the other ones, why they're wrong, you can do that, right? You can see that all of these, when you do, they will make the reaction go to the right. You want me to do that? Huh? Yes? Okay. Well, let's see C, right? You add more, oh no, we need to do it actually. Yeah, it's good to do it. We add more of B, which is a solid, right? Look, and maintain the volume of the gas of the mixture the same. Almost virtually all the general chemistry books, they will not tell you about the same time the volume stays the same. If it doesn't stay the same, the answer is not correct. Because the books say to you, if you put the solid, right, it does not change then. Position of the equilibrium. Why? Because solid and liquid does not participate in the equilibrium expression. For that reason, it's very easy to really prove it. You see it? That will not change the position of the equilibrium. But this under a condition. When you put the solids in, the volume of the gases available, volume for the gases should stay the same. Otherwise, the answer is not correct. That is going to stay without changing the position of equilibrium. And almost all books do not go into that. And it's very confusing to students, okay? So, let's go to the other one. Removing A, which is a liquid, right? And maintaining the volume of the gas mixture the same. Again, it tells you the volume, under the condition the volume stays the same, right? You remove what? Liquid. What will happen to the position of equilibrium? Nothing. Nothing, right? Because liquid does not participate in the equilibrium constant expression. How about removing D? If you remove D, we'll go from left to right, right? Yes? So, do you understand this problem now? Yes? Well, let's put this question for this problem. How about if I add more B and the volume is fixed? It's a container, right? I put a lot of B inside and the volume of the container stays the same. Remember, the volume of the container, the volume of the gases, it's not the same thing. Imagine a piston, right? So whenever I do these changes that the problem says there, I maintain the same volume available for the gases. So if I put a lot of B, let's say, in, right, the volume available for the gas is going to decrease, isn't it? Unless I increase the volume, like a piston, and maintain the same available volume of the gases, the equilibrium, the position of equilibrium is not going to stay the same, depending, of course, on the equation. So let's say I increase the B, I put a lot of B in the system, right? A lot of B, and the container is fixed. What will happen to the available volume of the gases? It's going to become smaller. And if it becomes smaller, it's just like I'm compressing it. Same thing, really. Even though I didn't compress it, by putting solid or liquid in, the available volume of the gases is less. So now it's like I'm compressing it, actually. And therefore, the position of equilibrium is going to change. Which way? You want less, so it's going to go and produce even more? Yeah. So if I put, let's say, liquid A, guess what's going to happen? More air is going to form. Do you get it? Because the pressure is going to go up. It's like compressing the system, right? The pressure is going to go up, and the system is going to move towards to have what? Less particles, gases. So if I put liquid A, in fact, what I'm going to do to the system is without, right? The container is metal, does not change. Actually, it's going to produce more liquid. Okay. How many people understood that? Raise your hands. Okay, it's pretty cool. You will not find it in the books out there. Isn't it? And it's very important, really, to learn how this thing will work. Okay? Okay, let's go to next. Well, you know the next, right? If this is quantitative or not. How do you know? Well, one way to say it is we have a strong acid. H3O plus is actually the strongest acid from all weak acids. You remember what we said? H3O plus is here. All the strong acids are above, and all the weak acids are below. So H3O plus is actually the stronger acid than any weak acid, and weaker acid than any strong acid, right? So it's actually this reaction is the reverse of the ionization of acetic acid. Ionization of acetic acid has a Ka of 10 to minus 5. Well, that's a very small one. And if you reverse it, it's going to be 10 to the 5th. So this reaction is 10 to the 5th. That's a pretty good equilibrium constant, large enough to give you a quantitative reaction, right? This is what already we answered that. Which of these following acids is stronger than H3O plus? So, look all these acids. Which one is going to be stronger? So for 2, the answer was B. It's for the sake of future viewers. For 3 is A. And for 4, what will be the answer for 4? So an H3O plus, stronger than H3O plus is only the strong acids. So which is strong acid here? Only this. Everything else is weak acid. Okay, so if you remember that order? Everybody got it, right? Okay, should we move to the next one? Well, this is a good one. How about this one? For any aqueous solution, the lower the concentration of H minus, what will happen to the pH, concentration of future class, Kw? So by changing the concentration of OH minus, goes down. This is the way to see it easy. For it, the lower the concentration of this will affect the pH. pH will go up or down. And Kw, how about H3O plus? Concentration, up or down? And how about this? Up or down? That's basically what this problem asking you, right? So when you see this multiple choice, it's good to do this, right? Write a few things down like that so you can think, right? So when this goes down, it's asking us pH, Kw, H3O plus, are we going to go up or down? So the question is, okay, well, will anything happen to Kw? No, that depends on the temperature we said. So forget about that, right? We will not change. How about when OH minus goes down? If when OH minus goes down, H3O plus has to go up because the product is a constant, right? So we erase this. And when the OH minus goes down, what happened to the POH? What happened to the POH? You remember that beautiful thing in the reader? Huh? Happy writing. What happens to POH? Because POH is minus log, it goes up. Up. Do you remember that? Goes up. And because POH plus pH is constant, 14, right? It's 25 degrees Celsius. If POH goes up, what happens to pH? Goes down. And so if it goes down, we erase this, and there you are. And though the answer will be 5D. Can you see how we did it? Huh? Did you like the way we did it? Pretty cool? Yes, we like it? Yes, we like it? We like it. Go to the next. Which of the following salts will produce a basic solution? So which of this is basic, right? Again, remember? If it's going to be basic, it should come from a strong base and a weak acid, right? So you examine all the salts, and what do you say? Ammonium chloride. Ammonium chloride. It comes from ammonia and HCl. Is that right? Sodium nitrite. This comes from sodium hydroxide, and this comes from nitrous acid. Ammonium nitrate. This comes from ammonia, and this comes from nitric acid. Barium dichloride comes from barium hydroxide, and this one comes from HCl. And sodium chloride, comes from HCl and sodium hydroxide. Okay, so strong and strong will give you neutral, right? Strong and strong, neutral. Strong and weak, weak base, strong acid, that's going to be acidic, right? So this is acidic. This is neutral. This is neutral. Neutral, neutral, because it's strong, 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 strong. Strong acid, weak base. It's going to be acidic. Okay? This one is what? Strong base and strong and weak acid. Oh, strong base and weak acid. That's going to be basic, right? So this is basic. That's great, great, because this one is going to be strong, right? And this is weak. So strong acid is going to be acidic. Okay, so the only answer is sodium nitrite. It's going to be basic. You see how we do it? Pretty easy, right? Okay. Let's go to the next. Oh, the next one is a good one. Okay. How about this one, number 7? So 6 was B. Okay, how about 7? To do this kind of problems, if you understand this type of problems about basicity, acidity of this kind of organic molecules, when you go to organic chemistry, you will do pretty well on the first midterm, because that's what we teach. The first midterm is full of these problems. How the strength of an acid or base depends on the structure, the connectivity of atoms, what elements, and the atoms of different elements, where they are located, far away from the basic side and the acidic side, or close to basic acidic side. Okay, and how many atoms, let's say electronegative atoms, are close to the acidic or basic side. Okay, so in this case, you have to really write them a little bit by extended form. So let's take the first one. F3, CH2, COOH. You can see these also like this. And then the other one is CFFH, and then immediately you go to this. And the other one is CHHF, and the carboxyl group. Then you have CF3, 3 fluorines with the carboxyl group. Then the last one is right? So now, this is a general principle here, okay? Let's say you have an acidic site. This is the acidic site right here. Do you agree with that? That's the acidic site, because as a Burstyn-Murray acid, we're talking about Burstyn-Murray acid base, it can be given off to a base. So that's the acidic site. This is going to leave as H+. Do you agree with that? It's going to go away as H+. This is the easy way to do it. The more minus charge is going to be here. Here is going to be a minus charge when it happens, yes? So when the acid is going to be stronger, when is going to be a lot of minus charge here or less minus charge? Less. The less minus charge is going to be easier to break away, and it's going to be a stronger acid actually. Okay? Kind of intuitively now. Later on we'll talk about Gibbs energy, that it's going to be better to explain it that way. But now intuitively you can do it that way. So, because all of them, when the H+ goes away, there will be minus, it doesn't mean it's really -1, all of them. They are about minus, because that minus charge on this oxygen depends what's happening on the rest of the molecule. On the rest of the molecule. The rest of the molecule, the rest of the molecule, the rest of the molecule. Can you see that? How many, even though when you write the structure, you always have O minus, oxygen minus, anion, yes, acetate. Nevertheless, the rest of the molecule is different. And the rest of the molecule, the more electronegative elements it has, that means their cyclic electrodensity minus charge to their site, the less minus charge is going to be on the oxygen. Yes? So, fluorine is the most electronegative element. It's pulling electrodensity away from the oxygen. So, electrodensity goes like this. like this, like this, like this. It's moving towards like that. You agree with that? Because the fluorine is electronegative. So now, the more fluorine atoms you have, the stronger the acid. Yes? And if you have a case that, and it depends on two things. How far the fluorine atoms are from oxygen. The closer they are to the oxygen, the more effect they will have to the acidity. Right? So it will be more, the closer the fluorine atoms is to the oxygen, the stronger the acid. Yes? And the more fluorine atoms that they will be wherever they are to the oxygen, the stronger the acid. You got it? So by considering all these things we said, which one will be the stronger? Which one? How many people say A? Let me see your hands. A, B, C, D. Good. Okay, great. You got it. Now, you got to be careful though, because now we also have the case of base. Yes? Huh? Well, almost all people raised their hands for the correct answer actually, which was 7D. After you consider the things we said. Okay? But before we finish with this problem, it's good to talk about what happens with the base. Because look, when you have a base, even though we don't have it in the exam, when you have a base, it's the opposite. It is the opposite. Because look, let's take a base with nitrogen, like let's say this one here. Okay, so the question on here is you have two bases, right? Why they are bases? Because they can pick up a proton, right? There's electrons here, and they can pick up a proton, and they can go into an ammonium ion, blah, blah. The same things, right? You agree with that? So, which is stronger? Everything is the same. Instead having here a hydrogen, this is a fluorine. You have 3 hydrogens here, you have 2 and 1. So instead of hydrogen here, 3 hydrogens, you have 2 hydrogens here and 1 fluorine. Can you see that? That's the only difference. So what do you expect now to be, which stronger now? Let's say A is this and B is this. Which is stronger? How many people say stronger base is A? Let's see your hands. How many people say B is the strongest? Let me see your hands. Oh, good, you guys, pretty good. You've been pretty good, okay? You want me to explain? How many people want me to explain this? Let me see your hands. Now there are more things. You guys don't know what it is. Look, this is the opposite now. The base is going to be strong when you have more minus charge here. Do you agree with that? Yes? More minus charge there. Which one has more minus charge? Because you have 2 electrons, like before, you have minus goes to pair of electrons. Which one has more minus charge? Because more minus charge, you will be able to pick up the H plus easier, it will be stronger base. Which one has more minus charge? The one which is like this, or the one that fluorine is sucking electrodensity away from it, like this? Shh. Electrodensity. Goes, minus charge goes away, because fluorine is electronegative. So if fluorine sucks minus charge to its side, then it reduces the minus charge here. Isn't that right? So you have less minus charge here from the electrons than there. Isn't that right? Therefore, this one is going to be stronger. And this is going to be weaker. The more electronegative elements you have, less minus charge here, you will not be able to pick up easier the proton. It's going to be weaker. Everybody got it, right? How about this one? What's the answer for this? Oh, you better know, because it relates something to your exam. Well, Which one is the answer for that? Which of the chemical species does not have a conjugate acid? Well, here's the question. Does this have a conjugate acid? It's a base, right? Conjugate acid means what? It can pick up a proton, right? And become what? Water. Is that right? Correct. Okay, so this can have a conjugate acid. The conjugate acid will be picking up a proton and goes, this is the base, goes, can this pick up a proton? It can have a conjugate, it has a conjugate acid. That's the way to see it, yes? Can this pick up a proton? Yes, so it has a conjugate acid. It will be produced when it picks up the proton, it becomes molecules of sulfuric acid, right? The sulfuric acid molecule, H2SO4, will be the conjugate acid of this base, hydrogen sulfide base, protonori base. Yes? Can this pick up a proton? There is a conjugate acid. It doesn't say it can pick it up. Is there a conjugate acid for that? Yes. Can HCl pick up a proton? No. Even though it's like this, and it has 3 pairs of electrons, yes, we know that this one, plus H plus, is not going to go and give you this. You will never see this species. Right? Even though there's a pair of electrons, it will not pick it up. There is no such a species. Right? So there is no conjugate acid for HCl molecule. Yes? Everybody got it? Okay. It's a simple problem, but it can be confusing, right? Okay. How about N9? How about, so A, the answer is A. How about 9? What's the answer for 9? Which is, 9 is really easy, it's just things we said in lecture, right? What's the answer for 9? C. The answer is C. The buffer solution has an acidic and a basic alkaline component. That does not have 2 alkaline components, right? They should not react with each other. That's it. Otherwise you're going to make it, right? A good buffer must always have equal concentrations. If you have equal concentrations, you have the higher capacity, right? And that's it. You know what? We are done. Okay? Good luck. Be enthusiastic. How do we do it? Positive, energetic, and enthusiastic. That's the way to do it.
So, hi everyone, we are here again. My name is Yuen.
Hi, how is everybody doing tonight? Good. Okay. That's good to hear. My name is Sherry, and yes, I'm wearing socks with my sandals.
We're going to sing 2 songs today, and the first one is Someone Like You. If you guys know how to sing it, just sing it with us.
Sorry. Okay, here we go.
That you're stay away, I couldn't hide it. I couldn't see my face, and that you couldn't hide it. I thought it isn't over. Never mind, I'll find someone like you. I wish nothing but the best for you too. Don't forget me. I think I remember you say sometimes you lost it love, but sometimes it hurts instead. Sometimes you lost it love, but sometimes it hurts never mind, I'll find someone like you. I wish nothing but the best for you too. Don't look at me. I think I remember you say sometimes it loves it love, but sometimes it hurts instead. Sometimes it loves it love, sometimes it hurts instead. Nothing compares, no worries, okay. Regrets and mistakes, they will remain. Oh, hello, how bittersweet this is. Someone like you, I wish nothing but the best for you too. Don't forget me. I think I remember you say sometimes it loves it love, sometimes it hurts instead. Sometimes it loves it love, sometimes it hurts instead. Which is number 9. The second song we're going to sing is Sunday Morning.
That's my roommate! Hi, Laura. You guys aren't roommates anymore.
No fighting. Sunday morning, rain is falling. Stood on the cover, shared some things. Sunday morning rain is falling and I'm calling out to you. Sing Sunday people, bring me back to you. Far away to get my soul back home.
Come on, everybody.
I'm waiting for I never want to be. Thank you guys. Good luck on the midterm tomorrow. And I'm sure we will see you during the final review session.
These two girls with a boy are creating a club. That will be a music club and also a poetry. They will have music and poetry. So an invitation is going to come out probably a few weeks from now, and you can respond to it. But in the meantime, if you want any information or you want to participate, Cherry is going to be putting her email, so you can email if you want to her. The point is, as I said to the other students in the other class, your parents invested money and time so you know how to play an instrument. A lot of you guys know how to play an instrument. Some people painting, some people athletics, whatever. Your parents spend time and money to really give you these resources, these beautiful skills. And when you come, and the reason they did that is because it balances their lives. You balance their lives. You came to campus with so much pressure, right? You got all these pressures, you're going crazy basically, and you forgot to practice what you learned in high school. Maybe some piano, maybe whatever, guitar, whatever. You just put it on the side and you just go crazy with thinking about your grades. You cannot succeed to make good grades unless you balance your lives. These two girls is an example that they did not forget what they learned in high school, what their parents invested for them. And I'm pretty sure that your parents invested for you on something, athletics, maybe art, maybe music, whatever it is, right? So here's an opportunity to join the club. It's going to be poetry, music, probably dancing too, okay? To recall these things, to start doing it. Because here's a statement. If we allow ourselves to continue to be gloomy, someday this world is not going to go for the next day. And this is a very serious statement. This world can be saved only by people that are excited, they know the power of gratitude, and they know how to balance things. If we don't learn how to balance things and we're gloomy and we're thinking only about the result, as our society is pushing us to do, this world is not going to continue for too long. We don't realize it. And it's not what will happen tomorrow. Whatever happens, we are not happy. We are not really enjoying life. So how about if we balance our lives? You do your studies, and you do some beautiful things you already know how to do things. Athletics, music, dancing. We just constantly see and we hear music. That's our culture, right? In the old days, all cultures, people were participating. They were dancing and singing, touching each other. Okay? That's what they were doing.
Now we're just sitting like this and we listen to music even here on the home. There is no life like that. There is no life. There is not communication. There is just isolation. Passivity and isolation. We need to connect with each other and we need to get excited, because if we don't, not only you will not do well in your exams, but in general life is not going to be pretty. So hopefully you take this message seriously, okay?